Okay, so we're going to now start to look at how we assign oxidation states or numbers, right? I'm going to use the terms interchangeably. They basically mean the same thing. This list here is, I have it in a bigger form on the course topics page. I think it's like useful documents for Unit 3. You don't have to memorize this. You will have it when you do the test. And remember, the whole idea of assigning oxidation states before we get into it is we're trying to figure out ownership of electrons in a compound. So if something has a positive oxidation state, that means it's electron poor or does not own electrons. If it has a negative oxidation state, it's electron rich and thus does own electrons, right? And the greater the magnitude, the greater the positive, the more electron poor, the greater the negative, the more electron rich. All right, so I'm going to read through these and then we're going to apply them. A free element is assigned a zero oxidation state. So basically, any element is always going to have a zero oxidation state, and the reason behind that is because even if it's a molecular element like oxygen, no one atom in the element is going to have molar ownership because they're going to be the exact same atom. If it's a single element, then it's just one element, so you can't really talk about ownership within a compound because it's not a compound. The sum of oxidation numbers in a neutral compound must equal zero. There's another one down here somewhere that if the sum of oxidation numbers in a polyatomic ion needs to equal the charge of the polyatomic ion, we're going to see that. Basically, when we're looking at ions, and I'll kind of summarize some of these here, when we're looking at ions, the oxidation number is the same as the charge. So lithium plus would be a +1 oxidation number, iron 3 +3 oxidation number. Let's see, compounds, group 1 elements. So yeah, I'm just going to kind of skip over this one. We already talked about this one. Sum of polyatomics needs to equal the charge. Oxidation number in halogens is usually -1. There's going to be some examples where that's not true. Fluorine is always going to be -1. It's the most electronegative atom on the periodic table. Oxygen is almost always going to be -2. This is going to be a helpful rule for us. There's only one small exception where we have peroxides, where oxygen is actually a -1, and the only peroxide you're going to see is hydrogen peroxide, H2O2. But for our purposes, basically oxygen is always -2. And again, it's very electronegative. It likes to own electrons, so it makes sense that it would have that negative oxidation state. Hydrogen is almost always +1. A couple of unique examples, but in our case, I think it's always +1 here. And so as I go through a couple of different examples, I'm going to zoom out for a sec. As I go for a couple of these different examples, we're going to build on this, right? So if you're looking at this, like, what's the point of assigning oxidation states? When we think about redox reactions, the whole idea is after we assign oxidation states in an actual reaction, then we can follow the flow of electrons as something is being oxidized or losing electrons. The other thing is being reduced or gaining electrons. Okay. And we also can assign oxidation states in molecules or ionic compounds. For example, this is a molecule covalently bonded of two nonmetals. So let's start to assign them. All right, oxygen is -2. In blue, I'm just going to do of each individual, and then in red, I'm going to do of the total. So -2 per oxygen, so we have -4 altogether. So carbon, it's net neutral, right? So it's 0. The compound has no charge, so that means the carbon has to be +4 so that it can, I guess, counteract or neutralize the negative oxygens. So again, when we're talking about this compound, what we're saying is that carbon is electron poor, oxygen is electron rich. I'll just draw this out really quickly just so you can get a sense of what we're doing here. So this is CO2, put our lone pairs there. And basically what we're saying is since oxygen is more electronegative, when we looked at this last year, it's drawing those electrons away from the carbon. And these arrows indicating sort of movement of electrons. And again, we'll get into this a lot more later when we look at bonding. All right, next compound. We have fluorine, always -1, and that means -6 altogether. So that means our sulfur has to be +6, right? So they're making that neutral. Okay, take a look. We have a -1 charge here. So now the sum of the oxidation states between the nitrogen and the oxygen have to equal -1. Oxygen is still -2. So it's -6 overall. And that means we have to have +5. So it's +5 overall, right? So this equals -1, which again matches our charge. All right, the chlorate. I just picked this one because chlorine is a halogen. It's usually -1, but when it's bonded to a very electronegative oxygen, actually it's going to take on a positive oxidation state. This is exactly like the one up here, so I'm just going to do it quickly. The only reason I included this one is just to show you that halogens can sometimes have positive oxidation states if they're bonded to really electronegative atoms like oxygen. Okay, now this one, I would say try this. I'm going to go over this one, but pause it, write it down, see if you can do this on your own. They're kind of a you try type thing. Okay, maybe you've paused it, maybe you haven't. If you're still watching, let's go through it. It doesn't really matter which order that I go through, and it's all pretty straightforward. The only thing that's a little bit tricky is iron can be +2 or +3, depending on really if it's iron, if it's iron 2 or iron 3. So I'm actually going to do this one last and go through all the ones that we know for sure. All right, so oxygen is -2, hydrogen is +1. I have 6 of them, right? So overall, I have +6 from the hydrogens, and I have -12 from the oxygens. Sodium is always going to be a +1. Again, that's the ionic state that it takes on, so it's overall +4. So if I look down here, I have +10, and I have -12. My overall state is 0 since this thing doesn't have a charge on it, so that means my iron has to be +2, right? So we have +12 minus 12 equals 0. So there you go. All right, now let's put this into context. Why does this stuff matter? I'm going to zoom in here so you can see this. This is a problem from your book. All right, I guess I'm not going to be able to zoom back up. Okay, so I'll just read this so you can see it. Metallurgy, the process of producing a metal from its ore, always involves oxidation reduction reactions. In the metallurgy of galena, lead sulfide, right here, the principal lead-containing ore, the first step is a conversion of lead sulfide to its oxide, which you're seeing right here. The oxide is then treated with carbon monoxide to produce the free metal lead. For each reaction, identify the atoms that are oxidized and reduced, specify the oxidizing and reducing agents. So I'm going to go over these terms as we look at this problem together. All right, and this is, an important reaction as far as getting lead mined from the earth, and really a lot of different metals we mine from the earth is a similar type of process, where we're roasting them and then we're using some sort of redox reaction to purify them in the elemental stage. I'm going to just write this bigger so we can see it. So this is the first reaction. I'm going to, oh shoot, there we go. It's a capital S for sulfur. Just going to zoom out this slightly. Okay. All right, so the first thing we want to do is assign our oxidation states and see how they change from reactant to product side. So I'll do that. Sulfur is going to be 2- because it's in the ionic sulfide form. That means lead is going to be 2+ because, again, it's neutral. Now, this is tricky. This is elemental oxygen, right? Elemental oxygen means it's going to have an oxidation state of 0. Another way to say that, neither oxygen in this compound has any ownership of the electrons. Okay, now we're going to look at our product set. This is 2- now, and this is 2+. So the lead hasn't changed, right? But take a look at our oxygen. It's gone from a 0 to a 2-. So it's gotten more negative. And let's look at our sulfur here. This is 2-, so 4. This is 4- altogether, which means that this sulfur now has to be 4+. Okay, so now let's take a look at what's actually changed. The sulfur has gone from 2- to 4+. It has got more positive. So that means the sulfur, if it's going to go from negative to positive, it has lost electrons. So the sulfur is oxidized. Now let's take a look at the oxygen. It's gone from 0 to -2. It's got more negative. So that means the oxygen has been reduced. Remember, reduction is gain. Think of oil rig. Oxidation is loss. Reduction is gain. All right. So our reducing agent is the atom that's been oxidized is called the reducing agent. I know, annoying term. So our reducing agent equals lead sulfide, and our oxidizing agent equals the oxygen. Oxygen is a very, very common oxidizing agent. This is why it's so reactive, because it's so good at being the oxidizing agent. Simpler to say it, it's really good at being reduced. Oxygen in the molecular form likes to grab electrons. It's more stable in the 2- form. Because it's so electronegative, it likes to have electrons around it. And then the last thing that I want to show you is now we can use this to figure out the flow of electrons, right? This is sort of the whole idea of redox reactions. Which way did the electrons move? Well, if our sulfur was oxidized and our oxygen was reduced, then we're going to have a movement of electrons in this direction. So the sulfur is essentially contributing electrons to the oxygen. And if we were really fancy and we put this in sort of different half cells like you saw in that GIF, then we could actually make like kind of a circuit from this, although not the case in this reaction. All right, let's do the second one. All right, so then the second reaction is we're taking this lead oxide up here and we're going to further react it with carbon monoxide. I'm just ignoring the states just to simplify this a little bit. And making lead making our free lead, which is the whole process is 4, and carbon dioxide. Okay, so then I'll apply our oxidation states. -2 plus 2, -2 plus 2. Okay, so now lead is 0, right, because it's an element. -2, that means the carbon, we actually looked at this in one of our examples, is 4 plus. All right, so let's take a look. The lead has changed, right? It's gone from 2 plus to 0. Take a second to think about what that means. It's gotten more negative, which means it has lost. It's got more negative, which means it's gained electrons. So our lead has been reduced. Our carbon has gone from +2 to +4, so it's gotten more positive. It means it's lost electrons, so carbon is oxidized. So again, that means this is the reducing agent. Carbon monoxide is our reducing agent, and lead oxide is our oxidizing agent. And just to sort of do what we did before, we have flow of electrons, right? That means our carbon is giving electrons to this lead in this redox reaction. Okay, now, last problem I'm going to show you guys. We're going to look at all these different reaction types from last year, and what I said at the beginning of the lesson is we can actually better classify these now as redox reactions or not. So there's basically 3 types of reactions in all of chemistry. I don't want to say what they are yet because I want to go through this exercise and then we'll sort of recap. One of them is definitely redox though, right? All right, so like we said last year, we learned synthesis where we have 2 elements coming together to form one compound. Decombustion, the opposite, one compound breaking apart to form individual elements, or in this case an element in a molecule, but the idea there is this is breaking apart. Single replacement, where the copper is replacing the silver, producing free silver, and now a copper ion compounded with the nitrate. They switch places, right? Acid-base, we've looked at this before in this unit, H plus, OH minus, making water, and then our other product is an ionic compound, sodium nitrate. Precipitate reactions, we've looked at those a bunch. Combustion, right? So we have a hydrocarbon fuel reacting with oxygen to form our products of combustion, carbon dioxide and water, and then the last one is energy. If you've studied bio before, you'll get to this. This is a very, very famous combustion reaction because this is the combustion reaction your body is using to make energy, combusting glucose in the presence of oxygen. It's not like burning them per se. It's this sort of complex process called cellular respiration. I'll talk about that in a little bit. All right, let's go through each one of these. And again, you feel free to pause it or you can just watch, but try to figure out which is redox and which one isn't. Okay, the first one is hopefully pretty obvious. Magnesium, 0 because it's an element. Oxygen, 0 because it's an element. And then on the other end, 2 minus, 2 plus. So this is clearly redox, right? Redox. I'm just going to go oxidize and reduce and not go with oxidizing agent and reducing agent. So my magnesium is going from 0 to 2 plus. So this is oxidized. I don't know why I switched to pink there. Oxygen is going from 0 to -2, so this is reduced. Again, we're going to see this as a theme. Whenever we have oxygen in a reaction, it's really good at getting reduced, really good at taking on electrons. So synthesis are redox reactions. All right, let's look at decomposition. This one, I don't know why I picked one that was this tricky, but this is a peroxide. So this is -1. Rare case. And again, the only peroxide I'll have you guys know is H2O2, hydrogen peroxide. And then this is plus. So this one here on the other side, +1, and this is -2 and 0. So this is, like I said, this is more complicated than I'm going to really get into. I'm just going to point out that the oxidation state of the oxygen changes. It goes from -2 and it goes to 0. Again, I'm not going to get into what's oxidized and reduced here, but the fact that we have a change in oxidation state from one side to the next tells us that this is a redox reaction. This would be more complicated than I'd have you do on a test. I'd have you do more straightforward ones. All right, single replacement. Let's go through it. Copper is elemental, so it's 0. I'm just going to group my polyatomics, makes it a little bit easier. If you want to see the full nitrate oxidation state, you can go back and look at it. But overall, it's going to be -1 because it's an ion. And that means silver is going to be +1, again, taking on those ionic states. Now, it's an element, so it's 0 on the other side. This is going to be -1, and then copper is going to be 2 plus. Again, I know that because of this is -1 overall. Sorry, minus 1 individually, -2 overall. My copper needs to be 2 plus. Okay, so what's happened here? Copper has gone from 0 to 2 plus, so that means it's becoming more positive. It's been oxidized. And silver has gone from +1 to 0. It's become more negative, so it has been reduced. All right, so far we've seen that 3 of the reaction types we looked at last year fall into the category of redox reaction. Acid-base. Okay, this one we can apply oxidation states, but what I really want you to see is, I write this as HOH, is that really what's happening in these double replacement reactions, both precipitate and acid-base, is essentially you have ions kind of changing partners with each other. So if I sort of siphon this off, we're going to see that there's no change. Sodium +1 on both sides. Nitrate -1 on both sides. Hydrogen +1 on both sides. And then again, if I look at it as HOH, I can see it maybe a little easier. That's -1. Or if I want to look at it individually, the oxygen is -2. The oxygen remains -2 throughout the whole thing. All these are -2. Okay, so we have no change, not redox. So acid-base reactions are not redox reactions. They are in their own class of reaction. And we'll get into them later when we do our acids and bases unit. Precipitate reactions are going to be the exact same thing as acid-base as far as redox is concerned. Sorry if these are hard to see. It doesn't really matter. None of these are changing. And this is kind of why when we were doing making our products, I was like, make sure that these charges don't change, which is, again, true when we're looking at our double replacement. So this is not redox. Okay, combustion. Assigning the oxidation states of glucose is tricky. I think I have like a longer description of this if you're curious. But oxygen is -2, hydrogen is +1. Carbon in this case is 0 for reasons that are a little bit complicated. Again, I wouldn't expect you to know that. I'm just telling you here. Oxygen is 0, and you're probably getting the point here. If oxygen is 0, then it's probably going to be reduced, which is exactly what happens. It's -2 on the other side. +1 for the hydrogen, and then this, we've done CO2 a couple of times, now it's 4+. And I haven't done any of the electron flow stuff, but I'll just do it for this last one. So we can see here, the carbon is going from 0 to +4, so our carbon is oxidized. And of course, our oxygen is reduced. So really, when you study cellular respiration, which I think you'll probably do this year, maybe not because of COVID year, but at some point if you take more bio, you definitely will. It's this long, complicated process that has all these different steps and all these different organelles of the cell, but really, as you sort of get to it, sort of the big picture piece is that your body is doing a redox reaction. It's using all these different enzymes to transfer electrons from the carbon to the oxygen. And since this is essentially a spontaneous process, these are more stable, the products are more stable than the reactants, so your body is doing this to get energy. So it's literally, when you look at this process, the thing that I find so cool about it is that within your cells, you're creating a current, you're creating a flow of electrons so that you can produce energy. And again, if you've taken bio, if you haven't, you'll learn this later on, making this molecule called ATP, adenosine triphosphate. All right, so there you go. To summarize, so yes, combustion is also redox. All right, to summarize, we have 3 types of reactions. Redox is one of them, and that includes synthesis, decomposition, single replacement, and combustion. So the more sophisticated chemist you are now, you know that all these categories fall under a redox. And then our other 2 are acid-base reactions and precipitate reactions. You could both classify them as double replacement reactions, but the chemistry is distinct enough, especially with acid-base reactions, that they do merit their own category. All right, so now go take a look at that homework and start to solve some problems.